So now we move on to the dynamics of the rigid body. That is the next step. So we need to introduce the definition of the angular momentum. Angular momentum for a collection of particles, right? And this is it's rather obvious. If you have a collection where I goes from 1 to capital N, you simply the angular momentum of this collection of points is just the sum. So remember Einstein convention that it's implicit here. So you take the position of each of these. So this is a cloud of this is di, or this is mi, and so on and so forth, right? You just take so this one has a certain velocity vi. And then there is another one here with a mass mj, a velocity v sub j. So you just sum over all these possible, all your collection of points, and that defines a quantity, right? That is a vector, and is what you call the angular momentum. It's just if you just have one, this is exactly a definition. This is the linear momentum, right? mv cross the position with respect to a certain point, Ri. So let me massage a little bit this this quantity, because you see this is a collection of points, but by assumption, right, they are part of what we call a rigid body. And we said that the rigid body, it moves about some axis with some angular velocity. That means that this velocity here, actually all the velocities that you have around, right, all these velocities, v sub I, can be written as this. So this is rotating somehow about some axis that I don't know, with the angular velocity omega. And so if I have omega, then you understand that the velocity of a point here, right, vk, is you take the distance, you take the distance from that point, and is cross ri, right? This is the velocity of that. So if you implement this, that is characteristic of the rigid body, then you have here a triple cross product. You remember that, so let me rewrite this. So you have sum over m sub I, then you have this Ri cross omega cross Ri again, right? And you remember that if you have three vectors, A, B, C, right, you have cross A cross B, C. Do you remember what that is? Yeah, A dot C in the direction B minus A dot B vector C, right? Well, I can never remember, but that's why I wrote it here. But it's in the back of many books. So let's just do this trick. I mean, it looks nicer this way because you just have two vectors. Here is a triple cross product, so this is not so obvious what it is. Well, the mass stays the same, but then you see B here is omega, so I pull out omega, that is B, and then I take the scalar product of these two, but this is the scalar product of the same vector, so it's just a square. So it's Ri square, okay? I don't know how to write it. This is now, it's a scalar quantity, okay? Because you take the scalar product of two vectors. So minus C, right? So C here is Ri, so this is the vector Ri. Then you have to take Ri scalar omega, so like this. So I'm just doing some, how it's called, this vector calculus, vectors algebra. This is kind of nice. This gives you the angular momentum of this rigid body as a function of this omega. And you see that you can write the component of this vector. So this is a vectorial notation. Usually when you do computation, I mean, vectors are nice, but when you have to do a computation, at the end of the day, you have to write down the components, right? Up to here, you manipulate vectors, but now if you really want to compute something, you have to go down to the components. And the components, so this is a three-dimensional vectors. It has three components, and I call this component Li, I guess. It's a different I, so maybe it's a little, it's a different I than that one. And you see, it's proportional to the component of omega, okay? But it's not linearly proportional. You see, there is some mixing. So it's true that you can write this as a omega, the angular, but you cannot put the I here because you see that this part it is, but this part not necessarily the x component, say L sub x in the x direction, comes proportionally to the omega component in the x direction. Is this clear? So here you have the problem that you are writing a vector as the product of a vector, but not component by component. So clearly here you have an object that is a tensor that we call IK. Is this the first tensor you ever seen? Yes? Did you see a tensor before? Yeah, so it's always Einstein stuff, so you have a sum over k. So the tensor is like a matrix, you see, because you have two indices. So if you multiply this by this, is a matrix times a vector. A matrix, so you multiply it by this to compute the first component. So a matrix times a vector gives you a vector. And the point here is that, you see, you are mixing the components of this vector here according to the matrix. So that, as I said, it's not true that the I component of the angular momentum is proportional to the I component of the angular velocity. They get mixed. You see that from here. You see here you have, for instance, you see the x component. This part is proportional, but this one gets all omega x, y, and z all mixed up. So if you insist on writing a vector like this by component, you cannot write simply a number here. You need a more complex object, and this more complex object is called a matrix. And the matrix, when it's a particular case of a tensor, when you look at the components, okay, and so this is 1, 1, 1, 2, 1, 3. Remember the matrix I wrote for the rotation, right? Then you go, so this spans the 3 by 3 matrix. So this I runs from 1 to 3, in this K from 1 to 3. Okay? So that's the general result, that your angular momentum is given by your angular velocity times a tensor. This tensor is called a second rank tensor, so a tensor of second rank, because it has two indices, okay? If you don't like this, imagine that you can have tensors of third, fourth, fifth ranks, you know, with many, many indices. And, okay, there are quantities in nature that, as I said the other time, there are quantities that are scalars, quantities that are vectors. In general, there are quantities that are tensors. And this is a nice example of a tensor. And we can, maybe it becomes more, maybe a little clearer. So I can write components of this tensor, right? So this tensor, the components are usually called moment of inertia coefficients. Okay, you see, it has to do with the inertia of the body, because it describes. you see it has the Ri inside, so it describes the geometry of the body. And is a sort of a generalization of the idea of mass. The mass is a scalar quantity and is the inertia of a point particle. If you hit the particle moves, right? And the way it moves is described by Newton's law, and the inertia of the particle in moving is given by the mass. If you have a distributed mass, like a solid rigid body, it's more complicated, and in particular you have a sort of inertia when you try to rotate this body, okay? And this is quantified by this tensor, okay? So if you look at, so I can look at a particular component of this, so this is a 3 by 3, for instance, I can look at the component in the x direction, right? The 1, 1 component of this tensor. And what is that? Well, this I see by inspection, so this thing is defined by this general definition. So you see the x, I have to pick the component in that direction there, and you see which one are those. You see, I take this equal to x, so I take the first component here, and also the first component here, right? So you see I have mi, then what do we have? I have is the first component here, but that I pull it out here. So I just have ri square, right? And here is a little more subtle because you see here I have so I have x omega plus y omega y and plus z. So I have to take this component in here, right? So I have the x component here, but I also have the x component there. So this must be minus x I square. Is this clear or is absolutely fog? Okay, good. You should write this. Right? Let's try and write this in an explicit. Maybe, okay. So this is mi, right? Then you have. I take the x component of this. I want to look at the x component. This is a right. This is a vector, so I look at the x component of that. So that is omega x. Then I have ri square. Okay. So x component. What is the then here? I have a more complicated object, right? I have minus ri vector, so I take the x component of that. So this is xi, okay? Then I have a scalar product. So there I have x omega x plus y omega y plus z omega z, okay? But I want to take the x component of this object. So I'm just looking, you see, is the part that is proportional to omega x, right? Because you see, I fix x, and so I take the x component of the vector, but I also fix this sum, so I must take the term that is proportional to omega x everywhere. So here, this was okay, and now this I don't want, I only want this. And if I collect, you see, this thing becomes mi r1 square omega x minus x. I guess here you have I square omega x. And now I factorize out the omega x to get what is, right? This is this, by definition, is I sub xx. Any improvement or still? Well, let's just check another component. For instance, what happens if I go off diagonal? I mean, this is the diagonal. So xx, xy, right? So how does that look like? xy, so again, I have to look at the, you see, I have to look to the omega, the term that is proportional to omega y now. So it's not this one, because this was the term proportional to omega. But in here, you see, I do have a term that is proportional to this. So it's this one. So it's actually simpler because it's just minus mi xi y sub I. So it's only this term here. You see, you have x sub I, y sub y, minus mi. And you can keep on going. In fact, that's a good exercise, and derive all the components. So I'm writing component by component this tensor. And each of these components is called, as I said, the coefficients of the moment of inertia that is this tensor. It's not that complicated. I mean, it's just that it gets a little more complicated than a point particle. That's why point particles are nice. And actually, the next level of generalization is that, okay, this is for a collection of point particles, but really the rigid body is a uniform distribution of mass. So I may as well replace, so as I said, this is a Einstein, well, this is too many. It's the Einstein sum implicit in the repetition of the same index, but as you may guess, if you go from a discrete distribution of masses to a continuous distribution of mass, you can replace this by an integral, right? You integrate over the volume of your rigid body. Let's say this is the volume of the rigid body. And therefore, this guy here is just the integral over the volume of what? The density of mass that we call rho. So this is the mass of the body divided by the volume. But you see, it may not be uniform. So it's a function of where you are in the body. So let's call it rho of r times this coefficient here. That now r is a continuous variable that you integrate over the volume. So it's r squared minus the x component of this. And you integrate over a volume, the volume of your volume of rigid body. And you see, this, okay, I don't have to write it down. It's just the same things, but only with the x, y here, and no r squared. In fact, I can now write the general form. So what is I, this tensor, this I sub ik? Well, by using this definition, is going to be an integral over the volume of your rigid body of what? Well, it has a r square, right? But only, you see, you have an r square only when you are on the diagonal of this tensor. So how do you encode this in here? Well, you use this Kronecker symbol that is 1 if these two indices are equal and 0 otherwise, okay? Minus xi and xk, meaning that now I wrote x, y, z as x. So x1 is x, x2 is y. Yeah. So that's the tensor in all. It's the full beauty of this tensor. And is what gives you the proportionality between the angular momentum of the rigid body and the angular velocity and the angular momentum. Okay, so it's like the mass and the rotation of this body. Something wrong? No. Rho is missing. You're right. Thank you. That's the density, right? Okay, so next step. So we want eventually we want to write the Lagrangian. So we want to write the kinetic. So this is the angular momentum. What is the kinetic energy under rotation? the kinetic energy under a translation, we already know that, right? You put all the mass at the center of a mass, and then it moves this way. We don't need this cartoon any longer. So what is the kinetic energy for this motion about some fixed point of your rigid body? Well, this is just 1/2 mv square, okay? That's always the kinetic energy. The only thing is that now, again, you have a collection of points. So let's do it just for the points. Then the generalization to the continuous distribution of mass is trivial. So I write it this way because I want to bring in this tensor somewhere. That means I want to bring in the angular momentum. So I write 1/2 mv square. I write it 1v. I write it like this, and then the other v I write it using the angular momentum, right? R I. Okay, and then I can go around, right? Because these things can be written as omega vector divided by 2 mi ri cross vi. But this is what? This is just the angular. Here there is this is just this quantity here. When you sum, this is just what we define to be the angular momentum of that collection. So you see the kinetic energy essentially is 1/2 omega L. And if you see, but L itself, right? We wrote L as the tensor times omega again. So in a way, if I write omega as a unit vector times the length of this vector, I can write this quantity as 1/2 the I that I'm going to define omega square. Where this I here is defined by, you take this unit vector and you take the scalar product of this vector to the tensor I. The tensor I wrote there. I don't know how to write the tensor. It's like 2 vectors, like this. But the meaning is that here you have ik, nk, and I. So you saturate both indices with unit vectors, and you get this nice result, that the kinetic energy of the body is, you see, it looks like very much is 1/2 mv square for the point particle. And here you can say that the kinetic energy under rotation of your rigid body is 1/2 the tensor of inertia, this quantity I here that I saturated and made into a scalar through this construction, times not v square but omega square. But they are the same thing in a way. That's why I was talking about the tensor of inertia is the generalization of your mass. So in a way, this scalar quantity that you extract from the tensorial one is the moment of inertia, but it's not just the general moment of inertia, it's the moment of inertia about this axis. Okay, so you define some axis and then you compute the component of this tensor about that, because you see what is this thing here. If I plug it back, is mi ri square minus ri scalar n. So you see it is taking the component of that tensor about this axis here, n, that you define. So if this is n, right, and ri is an arbitrary point here, you see I take the component here, this is r, I scalar n, right? And this distance here is ri square minus that component squared. You just use what is a Pythagoras triangle, right? R square minus that ri vector square. So you see this is exactly this component here. Now you understand what this is. You see it's really the mass distribution about the axis around which you are rotating, because that gives you how much mass it's here. This is mi, and how distance is this mass mi from the rotation axis. This is exactly the information that you need in order to quantify, if you wish, the inertia about the rotation. Right? Do you see that? So that's all we need if you have followed me up to this point. I have the kinetic energy, so I'm almost ready to write the equation of motion of this rigid body. But maybe we should compute some of these quantities just to have a feeling of what this moment of inertia is. So let's do that for a second, and then we conclude with the dynamics. So let's compute so what you want is an object, and then you compute the moment of inertia of that object, right? And so let's start from the simplest object. So I guess I want to write some examples of moments of inertia, what I call I. So so you remember, well, I erased it. Actually, let's put it here back. The V R square minus delta ik minus xi xk rho of r dv, right, over the volume. So what is the simplest mass distribution? Well, okay, we can discuss which one is the simplest, but let's take first a ring so this is the first example. Ring of mass m, big M, and radius big R. So this is it's a ring, okay, like a bicycle wheel without spokes, and the total mass of this ring is m. Okay, so this is a rigid body, and the moment of inertia, you see, it's a complicated tensor, and it depends, the coefficient of this tensor, they depend of the axis about which you are rotating, okay, first. And second, you do an integral, so it depends on the mass distribution of your object. So if you have a cube that has a different I than a sphere, for instance, okay? And also, if the object is not completely symmetric, it has different coefficients depending on the axis about which you are describing the rotation, okay? So all this is important information. So let's first start with so I want to compute the moment of inertia of this ring about this axis here. So it rotates like a ring, and it rotates like that. So it's like a bicycle wheel that you pull off the bicycle, and then you spin it about the hub, right? So then I have to compute this. It's just one component, right, because it's just the component about this axis. So and the axis go through the center orthogonally to the plane defined by the circle. So what is I? So since I define a single axe and a single geometry, then this is not a tensor now, it's just one number. It's just because I've done this projection. So what is this number? It's always, you see, it's a r square dm, you can write it, right? Where this r square, remember this drawing here, the r square is the distance of this dm. So here you have a infinitesimal mass hanging in there. This is the axis that you are rotating about, and this is the r of which you take the r square. So this is the definition of that. And then you just integrate over the entire volume this small mass here. But here the volume is very simple, right? So I can immediately write this dm is this r square. So what is r square in this case? Well, r square actually is a constant because it's 0 if you go inside. It's only different from 0. That is, you only have mass. The density of mass is different from 0 only if you are on this circle. So here, actually, little r is just this constant value of the radius of these things, right? And what is dm? Well, is the density of mass, okay, r d theta, right? Because it's just, here there is some density of mass, okay, r d theta. So this is the little dm, where this is d theta. Okay? Do you like it, or you don't like it, but well, that's life. And now, I mean, this is I have to integrate over the volume of these things, but the volume of these things is sort of trivial. Theta must go from, I don't know, 0 to pi. So now I only have to do this very simple integral. Everything is constant. Well, I'm assuming actually that the density, right? I'm assuming that the mass distribution is uniform because we want to do the integral. Otherwise, we need Mathematica. So that means that that if you want, this means that capital M is what? It's just 2 pi, right? 2 pi r, the density of mass, right? I mean, this is. So I do my integral, I get 2 pi r square rho, actually r cube, right? Because I have 3 of these. But you see, 2 pi r rho is just the mass. So this thing is just mr square. This is just mr square. So if you go back and you want to compute, remember the kinetic energy. The kinetic energy was 1/2 this I times omega square. So the kinetic energy of this object, when it's rotating about this axis that is orthogonal to the plane of this, is just 1/2 mr square omega square, okay, if you ever wonder. So if you go back to those problems that you remember on a slope, you had some masses rolling down. If now you promote your mass to a bicycle wheel, instead of writing 1/2 mv square, you should write, well, 1/2 mv square for the kinetic energy of the center of mass, plus the kinetic energy due to the rotation that in this case you just computed is 1/2 I mr square omega square, okay? But what is now this was rotating this way. What happened if I take another axis? So another coefficient of inertia, another moment of inertia. You see, now I take my bicycle wheel and I pull it up and I rotate it like this, okay? So this is another axis, it's the same system. Is the I going to be the same? Probably not, because you see I have to do the same computation, but now it's slightly different. So this is the same, this is just the definition, right? But now the problem is that instead of being a ring like this, right, is a ring like this, because I'm rotating about a diameter of my ring. So now I have to do essentially the same integral, right? The same integral. But now the r, remember that the r is the distance from the axis about which you are rotating. Okay? So now, before it was simple because you were rotating about the center, so this distance was big R. Now it's a little more complicated because you see the distance is this one here, okay? Is the component in that direction, right? So you see, when you are up here, this distance is not R any longer. Yes? Everybody? Yeah. Don't. I know that it's Friday and it's late, but it's not complicated. I mean, this is rotating like this, right? And I want to compute the distance from the axis about which you are rotating. So if it's rotating like this distance is constant. But now you have a disk like this, and you are rotating like that, right? Okay? So it's rotating like this. But you see now the distance of this point is this, while the distance of this is much bigger. So I have to take, well, this is just r, but if you go up here, you see it's a function of this angle. It's the sine of that angle time, right, times the radius. So now this r square is not big R square, it's big R sine of theta, where theta spans your circle square. All right? And then you have the mass density that is the same because it's the rho r d theta. So now the integral is a little more complicated, okay, because it's not just d theta, it's sine square d theta, okay, and that gives you an extra 1/2. Then you have the same 2 pi r rho, that's r square. So in other words, again, big M is still 2 pi r rho, so this is, so you see, is 1/2 m r square. So now the coefficient of inertia it's half of what it was in the original case because of this extra sine square theta that gives you 1/2 of what you had before when you did the integral. So I encourage, I think I won't give you any problems on that in meaning, no, I mean, wait a second before relaxing. But I encourage you to compute some of these quantities because that gives you a feeling. And in fact, I think, okay, we have time for, so let's do one more example, right? Then you try something. I write there a list of other objects that you so what would be the next level? What if this body is not a ring, but is a disk? Right? That's, I guess, is the next level of complication. So, well, okay, it's not a big deal. It's just that everything is as before. The only difference is that now this dm is not a one-dimensional integral, right? But it's you see, the dm, the little m, now lives in 2 dimensions. So that means that you have to integrate. You have to do this integral. The volume, if you wish, it's a disk, so it has 2 components. So you integrate two coordinates, not only the 2 pi, from 0 to 2 pi, the theta, but also from 0 to big R to catch all the mass that is inside. So you have d theta and then dr from 0 to big R, right? So that's the. But then it is the same thing. You have r square times so r square now is not big R, right? You understand? Because it's not fixed any longer. You have to integrate. And then you put the dm. The dm, again, is just, as before, is rho r, rho r. Wait, it's rho r dr d theta. I just wrote it there, okay? So you have to do this integral. Again, let's assume that the density is constant, okay? Let's assume that the density is constant, but now the density constant is not 2 pi r, right? Because it's a disk. So it should be pi r square rho, right? The surface of a disk. And okay, this integral, so you have to do first this integral here. You see, you have r cubed, right? And then the theta, it's okay because it just gives you a 2 pi. So what is it? Is r, so it's 1/4 is r to the cube. So I do the integral, 1/4 r to the 4th from 0 to r, so 1/4 r to the 4th, right? Times 2 pi from this, and we assume that the density is constant, so I can pull it out. So then I only need to rewrite this in terms of the total mass of my object, and the total mass is in here, then 2 here, and so you see you have a 2 that simplifies, right? So 1/2, then 2 powers of big R go into the mass, the same with the density, and so I have leftover of R square, if I did it right. So this is for the disk rotating about the central axis. Now a disk. So you see it's the same as the same inertia as the ring rotating by. And how about if I rotate the other way? So this guy here. Again, I have to be, this time I have to be a little more careful when I write this distance because, again, it's more complicated. And what I get is 1/4 of this. I'm sorry, 1/2 of this. So this I leave it as an exercise. So again, there is this 1/2. It's just that everything is 1/2 of what it was before. So if you wish, it's kind of odd. I mean, the disk is a half of the inertial of the ring, right? Because it was mr squared. This is 1/2. So maybe over the weekend, okay, it's supposed to rain, so why don't you check this? And another nice system to check is the thin rod. I mean, not because it's nice, it's just because it's simple. So a thin rod, it means you have, for instance, a wall or something, and then you have a rod of length L that can move, but it's kept, okay, it can move about this axis. So not the wall, I'm sorry, it's just about this axis.
What did you say 1/4 mr squared was for? A disk?
How did I get this? Or?
No, it's for which disk?
This is the same disk, but now, so 1/2 is for the disk rotating about the, I have here the picture. Now is the disk rotating this way. So it's a disk. So before it's like this, now it's like this. So again, you have to compute the same integral, but now you're not integrating, you have to integrate the distance from here to there. You see, it's not a constant here. Each time you integrate up to a point that is different, depending on theta. And, okay, another system is this one. I said, so a thin rod. thin rod of mass m, I guess, and length L. So if rotates about, so somehow it's kept fixed here, then it rotates this way. And if you do that, this is very simple. You get the I for this is 1/3 ml square. So check this, check this. And actually, there is a nice, then you can ask yourself, what happens if I rotate about the center of the rod? So the first one is if it rotates about one side. Then you can hold the center and rotate the rod. And in that case, you find that is 1/12, if I'm not mistaken. Yes. Okay, you can go. I mean, there is no end to but just check these three too. Well, I know that you have an exam on Tuesday, but this it won't take long. But okay, you can do it or not. I won't check, so I guess you won't do it. Okay, so let's go back. I want to finish this rigid body, but I don't think I can. But so maybe it will spill a little bit on Monday. But so we wrote the kinetic energy, right? So this you want it. Then we look into some examples of these coefficients that we introduce, and I mean, if we had more time, we could spend more time on that. I mean, this is traditionally one of the important examples of classical mechanics applications, but we sort of we do some sort of light classical mechanics. So. So in general, this to write this kinetic energy is complicated, right? Because remember, it's a tensor product. But you can step back for a second, and you understand that because you have this tensor, remember you can always diagonalize because the tensor is a matrix, and you know that if you find the eigenvalues of that matrix, then you can diagonalize the matrix, right? So that idea of diagonalization, eigenvalues, does not come from quantum mechanics, comes from here. The people have this matrix. That's the first place they had the matrix, and there they learn how to deal with matrices. You know, Heisenberg and these other guys knew about matrices because they passed their classical mechanics exam, okay? And so they knew that if you have a 3x3, like this one, you can find three eigenvalues and then diagonalize the matrix. So the same we can do it, right? Why should we deal with such a complicated quantity, 3x3, so 9 coefficients, okay, when we can simplify our lives? What is the physical meaning? So in other words, you have this Ix, Y, right? 3x3. So I have to write 9 of this. So X, Z. Then X. Well, this is Y, X, and so on and so forth. If you multiply by this minus I, then you take the determinant, and you solve this. You find three values. So physically, what is that? These are called principal axes. You understand that the components of this tensor depends, as you have seen here, of which axis you are considering in defining your components. Okay. So what makes this special is that you are finding in your body three axes for which when you compute the coefficients, they are all zero except about those axes. And this procedure assures you that you can always find these three axes that in a way is a choice of axes that make the tensor the simplest, because with only three non-vanishing components, okay? So it's a clever choice of axes. Very often, if the symmetry of the body is evident, it's very easy to pick the axis, right? Like before, we had a circle, and now think of a sphere, right? Then it's very simple to pick these axes because they are just three orthogonal axes, and that's all, right? So these are called the principal axes. If this is true, then your relation between the angular momentum and the angular velocity is particularly simple, right? Because it's just, say, 1 is, I call 1, 2, 3, the only three components that survives in this tensor after diagonalization. And so you see they are just all proportional in this case. So I can write my three components in this form. I write them, and then the kinetic energy is much simpler. I don't have to introduce this tensor. I just have these three components. So it's just 1/2 the sum of this, where I take the square of those. So I omega I square. Remember Einstein rule. And if you want to be precise, you have to add to this the total mass of your rigid body times the velocity, the translational velocity of the center of the mass. So now this is the kinetic energy of the rigid body, written using the principal axis of your body. So, okay, if you are given a body, then you have to identify the principal axis, and then you can write that. Then you compute this coefficient for these three axes, and then you can write most of the exercise that you find in the books. So, as I said, the geometry of your rigid body is very simple, like the sphere, right? I said it just, the sphere is trivial. I mean, it's completely symmetric. So essentially, these three are not only just three, but they are equal, right? Because it doesn't matter which way you compute. The sphere is always a sphere. So you just compute one, and then you have the result. Having said this, now I can write what is the equivalent of Newton's law for a rigid body. That I take it from is something that tells you how the angular momentum changes in time. So you need to know, right? Instead, what is the change of the angular momentum with time, right? And if you remember what we said about the kinematics, right? You have just it's not only the one computed in space, right? But you also have this extra component. Remember what we did? We said on Wednesday. And how can you change this? This you must know from your classes on elementary mechanics. The way to change the angular momentum of a body is what? The way to change the velocity of a point mass is to apply an external force, right? A force. That's Newton's law. What is the equivalent of a force for a body that is extended? How do you change the rotation? The torque. Do you remember this somewhere? I call it N. So this, as your colleague pointed out, is called the torque. Right? I mean, this is, if you want to change the center of a mass of this object, you apply a force, right? But if you want to start some rotation of this, it's not the force that you apply, it's a torque. That is a force times the distance at which you are applying that. Okay, it's a vector, is this. the torque. Did you remember that, or it's a new concept? Yeah, you never heard about the torque? I hope. Who never heard about the torque? Okay, now you did. So that's, if you wish, is the equivalent of Newton's law for the rotation. I don't know how to put it. Okay, you apply a torque, and then you have a change in your angular momentum. But let's rewrite. I mean, this is a sort. This is just to recall. It's just to jog your memory, because I start from that, but I really want to use my what we introduced. So I replace. If I now replace my definition of angular momentum in terms of the coefficients of your tensor of inertia, right, through the momentum. So I just take L from there, I replace it in here, so that I get my, so I take my principal axis, and you see that this L, these are constants, right? Once I've specified the axis, these are constants, so they come out. So the first term is just, right, this is the first term, I replace that. I need a new chalk. Plus, I have this vector product. Now I want to deal, so I have an omega, then I have the I, and then I have another omega. How do you write the vector, the cross product, I don't know how you call it, vector product, cross product, in terms of components? You remember this Levi-Civita symbol? Have you ever? This epsilon, I, J, K, right? Yeah? It's like the older brother of the Kronecker symbol, right? Because it has 3. And what is the rule? That you fix, I don't know, 1, 2, 3 to be 1, for instance. Then if you go cyclically around, you get 1, and it has to be completely antisymmetric. So if you switch 2 of these, you know, it must be, okay? So this allows you to write the vector product, and then I use it. So I is this I. Then I have JK that runs over what? The two angular momenta. So I said J omega K, and then you have a IK. So this is just a rewriting of the vector product or whatever in terms of component. So, okay. Is this right? IJ. No. It's no, but this is not summing actually. In this case, because here I want to put the Ni component of the torque. So this is an index that you keep. What? No, sorry. Yeah, no, it's JK. What did I do? Wait. No, but it's correct, huh? Because I'm not. I'm just taking component by component. It's correct. For instance, let me write one component. One component, 1 omega 1 dot. So I'm writing this. I'm not summing, okay? I pick the one component here. Then I take. You see, this is 1 now, right? So this should be 2, 3, or 3, 2, right? If they are equal, it's 0. If 2 are equals, it's 0. So I have epsilon 1, 2, 3. So omega 2, omega 3, I3. Then I also have the 3, 2, right? Minus, yes, the 2, 3. So minus omega 3, omega 2, I2. And this is equal N1. Okay? Do you understand how you read this? So you don't sum, you keep the component. So this, okay, let's. So if I now write these components. So this I don't need it. This equation in the language that we introduced today, it gives rise to three equations, one for each component of the torque. So N1 is equal to what I wrote there. So I1 omega dot 1. Then I can collect this because you see is minus omega 2 omega 3 I2 minus A3. And the N2, you just go cyclically, you understand, right? The I2, it just goes. So it's going to be I2 omega dot 2 minus omega 3 omega 1. Yes. I3 minus I1. And N3, the third component. So I'm just rewriting this equation. No, this equation here. Component by component. So this is I3 omega dot 3 minus the other two, omega 1, omega 2, I1 minus I2. Okay? So these are the equation for the change of the angular momentum given by an external torque. That is essentially all the dynamics, all the dynamical equation that you need in order to study the motion of a rigid body. And when you translate this equation in terms of the angular velocity and the coefficient of the moment of inertia with respect to the principal axis of this body, you get a set of three equations that they are so important they got a name, and it's not a big surprise, is Euler equations of motion. So in this context, these are the equivalent of Newton's equation of motion for the rigid body. And this is the Euler's, the same guy who wrote the Euler's angles, obviously. That's, now you see why he wrote those angles. So now we have the equations. We sort of understand the kinematics of the body. So now we can solve many, many different problems. But we don't have time to do that, unfortunately, with your relief. But what kind of problems? Well, there are many. They are all sort of interesting. So I start with one, and we finish it on Monday. So I want just to discuss one problem, at least, by using this. And it's a very important problem. At least historically, for the development of classical mechanics. So these are the equations. You understand that these are the equations, right? So if you have a Lagrangian, you get those equations. Like if you have the Lagrangian, you get back the Newton's equation. And you understand that the trick here is that it's not omega 1, 2, 3, the generalized coordinates, because remember what we said about the kinematics. The generalized coordinates are the Euler's angles, right? So you first need to express these velocities in terms of your generalized coordinates. And then the solution of the problem comes through the trajectories of these angles. So let's try this in an example. Well, let's start and then we see how far. Do I need this? No. But you have two of the problems that you are going to solve for next Friday are on this. I'm sorry to say. One is, in fact, I think, let me just say, what is it? Yeah, one is exactly about this. I say 5.4 and 5.26, right? Do you remember? I think so. So one is exactly this, that I ask you to derive. Now I'm going to write this, how you go from the angular velocity from the velocities written in terms of the, but the exercise that you are supposed to solve for next Friday is exactly to prove what I'm going to write. And the other one is 526. Yeah, is to find the solution of this Euler's equation for a body axially symmetric, so that it's easier to find the principal axis, with zero external torque. So it's like the free motion of an axially symmetric body, okay, like a cylinder. Okay, so these are two applications. Now, those are trivial, well, but one that is not quite trivial, and in fact, we won't write exactly the solution, but we will discuss the quality of the solutions using this idea of the effective potential, is a very, you know what a top is, a spinning top? Have you ever had as kids, you know, the things you spin and then it rotates very fast. Now that's it's an amazing object if you think about it, right? Because as long as it spins, it just stays vertical, right? It doesn't fall. And also, if you perturbate the system, it tends to react, right? It's not that you push and it goes down; it comes back. Now, this is such a wonderful thing that people have been studying this in many different forms, and it has many, many applications because the point is, how to say, for instance, if why you are on a bicycle, right? And if you are at rest, it's very easy to fall, right? If you try, like if you stop at the red light, you have to put down at least one leg, otherwise you fall, right? But how come that as long as you move, there is no problem there? I mean, the bicycle is very stable. Have you ever considered about this? This is the first thing a kid should ask. If you are going to be a physicist, this is the first question you should ask. The first time you try a bicycle. Why, as long as you pedal, right, as long as you push, the bicycle is very stable. In fact, it's even hard to turn. If you try to turn, you have to apply a torque effect, right? Because the bicycle by itself, in fact, you can pull out your hands, right, and then it keeps on going, more or less, sometimes less, sometimes more. So why? How come? The point is that it's spinning, right? And there are beautiful properties. Essentially, a spinning body keeps on spinning. And because it's spinning, it's very hard to modify the axis about which it's spinning. So if it's free, it has it's not. It's called a gyroscope, right? So if you take a disk like the one we compute, and you start spinning this disk. If the friction is very low, this thing keeps on spinning. Or maybe you put some energy in it and it keeps on spinning. That is a beautiful system because you see it identifies a direction, it tends to keep that direction. Because if you you apply a torque, sort of go back. I mean, it's hard to push it away. This is the way, for instance, the inertial navigational systems work. For example, if you want to send a satellite on the moon, or even farther, you know, people have sent satellites even outside our solar system, how you keep the satellite in one direction? Essentially, you put a gyroscope inside so that the system is stable. Otherwise, it tends to wobble and it will tend to. And that's also the way navigational systems, you know, before the GPS, how did the airplanes knew if they were going in one direction rather than going in, you know, turning around? They had these inertial guidance systems that they were based on a gyroscope. Gyroscope inside the airplane keeps a fixed position, a fixed direction. So if the plane tends to, they know, because then, you know, there is a torque, they measure the torque, and they know how much they have deviated from the original direction. So that's a gyroscope. How about the top? That's a nice system, and also we would like to understand, because, I mean, if it's not spinning, then it falls, right? Well, I don't have a top here, but essentially if I put it like, well, it falls. But if it is spinning, then it's very stable. So how do we understand that? Well, that we need, we need the Lagrangian. So this is called the heavy because we put the spinning top in a gravitational field. That is the situation. And we take a top that is symmetric, right? It has it has a axial symmetry. So it's called the heavy symmetric top. Okay, so this would be a gyroscope, but I put it with one point fixed. So again, I'm not very good at drawing, but so it's something like this, right? So this is the axis I call Z of symmetry. Here's the fixed point, right? It's spinning. So it spins about this. And this axis is not necessarily, this is the vertical, so gravity is this way. So I have a theta angle that is going to be one of my Euler angles, right? And this guy is spinning. And here at the center of the mass, you have your gravity pulling down, okay? So as I said, this is historically, they have studied these problems because it was fun, and also because it teaches us something important. Okay. So so this is the vertical direction. In a way, I have already identified. I need my degrees of freedoms. 3, right? And we already agree on Monday that we use the Euler's angles, and I already identified one of the 3 Euler's angles to be the angle between the vertical direction along which gravity is acting and the axis of symmetry of my spinning top. Okay, so the other 2, you remember, you need. So here you put, I guess, so you have. So you remember, you sort of turn this up, and you rotate about this. So this is what I call phi. Phi is when I rotate like this. Then I rotate to go this direction, and this was, I call it psi. Remember, we I introduced the Euler's angle. And now I want to write the Lagrangian, right? So we are back after this long detour about the rigid body. We go back and we want to write the Lagrangian for this system. And then on Monday I will discuss the solution. So how do I write the Lagrangian? The Lagrangian is the kinetic energy minus the potential. By now you must be sick of this, but we are moving to the Hamiltonian next week, so bear with me. But okay, but think of solving this using the equation of the torque. I mean, you hate that. I mean, it's much more complicated because you write all the components, you have to figure out the torque. What is the torque here? You see, this is the force, and this is the arm, right? All this. Very complicated, but we don't have to worry about that because we developed this technique. I only need to write the kinetic energy, but the kinetic energy, I just wrote it, right? It was the 1/2, the sum of the coefficient of the moment of inertia with respect to the principal axis that now we are going to identify, very simple in this case, times the square of the angular velocity. So I can do that, 1/2. Now, notice that, so it will be I1, I2, I3, but if I call you see, there is a symmetry here in this body, you understand, it's an axial symmetry, right? So clearly two of the principal axes, the one that are define in the symmetric directions are going to be equal. I mean, if about this, about that, they are going to be the same, right? It doesn't matter. So clearly, I can already write a single, let's call I that principal axis in that plane. So omega 1 square plus omega 2 square. So I assume that I2 is equal to I1. And then I have one that is the surviving one that is about the other direction that is in general different. If all three were equal, then I would have a sphere. But I don't have a sphere because, you see, I have an axial symmetry. I mean, everything about this axis is the same, but it's not true that it's the same along that axis. So for that one, I have to keep, so I need I3 and I1. I'm not going to compute this because I leave the shape of my top arbitrary, it's whatever it is. If you give me the shape, I'll compute the I. But you understand, if this is the shape, you are going to need a Mathematica or something to compute it. If it's just a cylinder, then you know how to compute it, right? But in general, you need you have to do it numerically if the shape is a bit complicated. But we don't care. It's just a number. It's like the mass. It's like the mass of a particle. We don't need to know that mass is 1 kilo rather than 10 kilos to solve the problem. As I said, now, well, and then the potential. Well, the potential is very simple because the potential is like if you had all the mass of these things concentrated in the center of a mass. So let's call, I guess I call L the distance of the center of a mass from the fixed point. In that case, the potential, right, is just m, the total mass of that spinning body, GL cosine of theta, as usual. Where theta is that. So as I said, to proceed from here, I need the general formula that gives me omega 1, omega 2, and omega 3 in terms of my generalized coordinates. And my generalized coordinates are the Euler angle. So this is the exercise that you are going to try and solve for the next time. I give you here the solution. So these are angular velocities, and when you write them in terms of the Euler's angles, you get some weird combination. This is a psi. Okay? So either you take this because I said it, or you read it off from any textbook of classical mechanics, or as I suggest in the exercise, you derive it by yourself. Just remember this A, B, C, remember those matrices. We compose the general rotation matrix through components, so you should follow that hint. I don't know if this is a hint or. So to write now, so the Lagrangian now, this is, let me write the Lagrangian, then I stop, is T minus V, right? So all you need is to square these quantities and put it there. And you see that, let's consider the first. So I have I1 divided by 2. Then I have to take the square of these 2. But you see that there is some simplification, because when you square this, first of all, you see there is some cancellation. Then you have the usual trick that you get sine square plus cosine square here, right? And here you get phi square sine square, then sine square cos square psi. So essentially the psi drops out because it's always in the combination sine, cosine, square. So so from this, the square of these two, I sum, I get theta dot square, right? Then I square these two, and you see that I get plus phi dot square sine square theta. Then these two sums to 1, and then the cross product simplifies because it's the same. You see, they have the same. Okay, good. So it's not that bad. And then I have I3 divided by 2. And here I cannot simplify anything because it's just this. So I just take whatever is given and I square it. And here you have the psi dot that was not there, square, minus mgl cosine theta. So this is the Lagrangian of the spinning top. And on Monday, we'll, the first half of Monday, we write the Lagrange equations. And as I said, I'm not going really to solve them because we are not going to learn anything more by finding the exact trajectories, but I'm going to write a sort of effective potential, you see. And you remember how we discussed qualitatively the orbits about the Kepler problem, right, to find open, closed orbits. And here would be the same in a way. We'll study this function, and according to the presence of or not of roots, we will see what is the general motion of this body. And it's very complicated. It's very complicated, this body, because it spins, right? And as it spins, it precedes. It's like the Earth. And as it precedes, it's nutation. It moves like this. It has 3 movements that we will find here. So, and they are characterized by this Euler's angle. So essentially, the solution, the general solution is, so it's spinning like this, okay. As it spins about this axis, it precedes. So the axis moves around this one, like the Earth, even though the Earth has no fixed point. And as it precedes, it's also moving back and forth, up and down like this. So very complicated, fascinating, and we will understand from this equation. Okay, so it's a beautiful system, and also it's important because by removing the fixed points, still it has some of this property, and this is what happened to the Earth. You know that the axis of the Earth is rotating, but it's not fixed. It moves about. It's preceding, and it takes like 20,000 years roughly to go around completely. Okay, so in a way, you know, now it's pointing roughly toward the North Pole. I'm sorry, the how's it called, the polar star. How it's called? Yeah, but you know, in 10,000 years it will move a little bit away, right? And also it moving like this. Also the Earth is nutating. This is even slower. Okay. Okay, that's I think I stop.